โอเคครับอาจารย์เราน่าจะเริ่มได้เลยนะครับอาจารย์แชร์สกรีนอาจารย์เลยก็ได้ครับผมอาจารย์ได้ยินไหมเอ่ยออกมาแล้วโอเคครับOkay, welcome everyone to NCAO 2020. This is the second day of our event, and we have 3 speakers today. And we have 2 in the morning. The first speaker is Ajahn Parinya Ngiamsunthorn from our Department of Mathematics at KMUTT. He will give a talk about differential equations, and today's theme is all about differential equations. Okay, Ajahn Parinya, you have around 50 minutes. You can use your time. You don't need to rush.
Okay, thank
Okay,
you.
so yeah, you can start. Thank you very much.
Thank you, Dr. Parinya, for the introduction. So today, the topic that I'm going to talk about is about the nonlinear analysis. We will focus on the differential equation, and the outline of my talk, right? Actually, in this talk, I want to outline some of the journey in terms of mathematics that I have been throughout the time that I study and also working right now. So the first part of the talk is about parabolic equation. I actually focus on partial differential equation. So the talk today will focus on partial differential equation, in particular, the parabolic type equation. So the first topic that I'll talk about is the one that I have been through during the time in my PhD, like so many years ago. Okay, and then you can see that at the beginning of my career in mathematician, I study about this parabolic equation, and later on, when I teach at KMUTT, I start to work on the topic of fractional equation, fractional differential equation. So the second part of my talk will be on that topic, on the time fractional evolution equation. And finally, in the last part, this is not the work that I have done, but it's just something that I'm interested to work. And I think this should be something that I will go to in my next career when I start to look at some optimization problem that involve solution of partial differential equation. So I think this should be the theme of this workshop, actually about nonlinear analysis and also optimization. So that's why I include the last part of my talk today. Okay. So let we begin with the one that I mentioned. This is the part of my early career that I start to look at parabolic equation. So let me introduce the idea of parabolic equation. So what I look during that time is I consider the domain, or this omega is an open bounded set in Rn. So this is the domain, some open set in Rn, and we consider this general form of parabolic equation. So you can see that the first equation in the equation 1 is about the derivative with respect to time t. And the second term here is the elliptic operator. And the right hand side is f of xt. So this x comes from the space variable with this the domain omega, and time t start from 0 up to capital T. So in here, the general form of the operator A is this elliptic operator written in the general form like this. And we prescribe the boundary condition in the second equation here. You can see that bt of uxt equal to 0 when x come from the boundary of the domain, and t from 0 to t as well. And the last equation is the initial condition. So when time t equal to 0, you prescribe the data u0 in the domain omega. Here, as I said, when I look at this parabolic equation, we consider two main type of boundary condition. The first one, the case when bt u equal to u, right? So you will get u equal to 0 on the boundary. That one is called the Dirichlet boundary condition. On the second case, when we consider this is the normal derivative. So this nu I is the unit normal vector dot product with the derivative of this form here. So the second case, when this term equal to 0, you get the Neumann boundary condition. So this is a general setting that I work on both Dirichlet boundary condition and Neumann boundary condition for this parabolic equation. But you can see that the special thing is that the operator A here is depend on time t as well. So this is kind of non-autonomous system that the system that it depend on time. But you can see that this one is not nonlinear. Actually, it's a linear equation because the right-hand side, the non-homogeneous term here, depend on x and t. Only the variable involved in the equation, but it's not depend on the solution u itself. So this is the simplest case when we look at the linear equation first, and then I will talk about later on when we consider some nonlinear case. All right. So some example that I think everyone should know that this is the type of parabolic equation is the heat equation. When this operator A here that I mentioned is just the negative of Laplacian operator here. So you get the equation du dt subtract with minus Laplace, subtract Laplace u equal to f like this. So this is just the simple heat equation. That is one of the form that when you have the operator A equal to the negative Laplacian. All right. So what I did with this one, because when we want to consider this equation, you can see that it's involved the space variable on the domain omega and the time variable as well. So we try to rewrite this equation in the abstract formulation. So we will consider the equation in terms of some function space. So instead of the two variable that we consider x, the space variable, and the time variable t, so we consider the unknown function u as the function of t only, because we think of ut has the value in some Banach space that depend on the variable x. So instead of considering the function with x and t, we reduce only to consider the function in terms of t, but the function itself is not in the real value function, but is in the Banach space, some Banach space. So we consider V is the Banach space. So this equation will reduce to only, we can think of it as like an ODE, but the value of the function itself is in some Banach space. So this is the kind of technique that we reduce partial differential equation to somehow is look like ordinary differential equation, but in fact it's not, right? It's the partial differential equation, but we consider only one variable t here. So the derivative with respect to t, so we can write u that. And the operator, this is the different operator that induced from the previous slide, and the function that in terms of t. So all of this value we consider in some Banach space. So the setup for this parabolic equation is depend on the boundary condition. So if we have Dirichlet boundary condition, we will use the Banach space to be the Sobolev space H10 on the domain omega. So the function ut will be in H1 of omega. So that means we have another variable x hidden in here. But for the Neumann boundary condition, we will use the Sobolev space H1 of omega, because H10 is mean we have compact support in the domain omega. That means it's coincide with the boundary equal to 0, right? So it's depend on the boundary condition why we choose this space. But the good thing for this Sobolev space that we have some properties about the space, because if we choose V to be either the H10 or H1 omega for this Sobolev space, we can embed the space into the L2 space. And if we identify L2 space by its dual, because they have the same dual, because L2 is a Hilbert space, then we can have this embedding for the space V inside the L2 space, and the L2 space embedded in the dual space of H1. All right. So with that, for the Hilbert space, we use the inner product for this notation, and the bracket here is the dual pair between the dual space V dat and V. So when we want to consider the solution, because the solution depends on time t as well, we need to introduce some space that depend on time. So we consider the Bodner-Lebesgue space here. This space, you can see that we call it L2 from the interval AB. So this is the time t variable. U is a function of t, right? But the value is in the Sobolev space or Banach space V. So we will call this one is Bodner-Lebesgue space. And since we look at the derivative as well, so we somehow look at the Sobolev space in terms of Bodner as well, right? So we denoted by W for the space that the function U come from the Bodner-Lebesgue space L2 with the value in V, but its derivative U prime here has the value in the dual space, right? So this one, the derivative that we consider is just in the weak sense or some in the sense of distribution. So that what we consider here is the weak formulation. So we are looking for the weak solution of that. So the problem is that we formulate it in terms of weak derivative. So this W, the space W here is a Banach space when we put the norm to be like the usual norm, right? The L2 norm in terms of Banach space V, and the derivative is in V that is dual. So we just put these two L2 norm together and then take the square root of this. All right. Okay. So the good thing of this Bodner-Sobolev space that is have the dense embedded in the space of continuous function on the closed interval AB, and it's linked for this Banach space V and V that is linked with the Hilbert space H for the evolution triple that I mentioned earlier as well. And also we have the integration by part formula. So it's like when you integrate from A0 up to B0 of U that dual with V plus V that dual with U, is just like you take UV and integrate from A0 to B0. So you put the upper limit of integration and subtract the value at the lower limit of integration like this. So this somehow we have the same idea of the integration of bypass formula. So basically what I did here for the setting, this is the standard setting that you can read through many textbooks in partial differential equation, in particular for the parabolic equation. This somehow is the idea that we change like partial differential equation to reduce somehow look like ordinary differential equation, and we just use the integration by part as usual to solve the problem. But the difference is that the function that we consider is not the real value function anymore, but it has a value in some Banach space. Okay. So here I want to outline the assumption for the parabolic equation that I consider. So we want to set up the form, the elliptic operator, we write it as a bilinear form that involves the time t as well. And these two components here come from the space V. Is the bilinear form on the space V. And we assume the following condition. The first one, if we look at t as the parameter, then the map t to this bilinear form when we compute a of t uv, this should be measurable function. The second one is that is the bounded property like this. We have the positive constant m, and this positive constant is independent of time, such that the absolute value of ATUV is less than m multiplied by the norm of u and the norm of v for all uv in the space. And the last one is like the elliptic condition, that we want this bilinear form to satisfy this some term that involve the Hilbert space H, lambda u square is greater than alpha times the norm in the Banach space V, like this. And with this assumption, we can get the induced operator AT that come from the space V, and the output is in its dual space V. That so AT is the continuous linear operator from V to V prime here for its dual space that you get from this dual pair here, AT of U dual with V equal to AT of UV, like this for all UV in V. Because when you take U in the Banach space V, AT will become the element in its dual V prime, right? And with the condition, the second condition here, you can get that the supremum of the operator norm is less than or equal to m. All right. So somehow this condition is we use to set up some bound in order to obtain the existence and uniqueness of solution. So let's come back to the equation. So when we have the equation written in the abstract form like this, and we consider in the space V prime here, so f will be a function from 0t up to V prime. So f has a value in V prime here, and the equation that we consider is in the dual space like this. So u prime also in the dual space, AT of u, as I mentioned, the operator will take you to the dual space V prime, and f has the value in V prime like this. So this is the abstract formulation of the parabolic equation. And the given initial condition, we consider the condition U0 in the Hilbert space or in the L2 space, like that. So the idea of getting weak solution is that we multiply by test function with this, because all the all the value in this equation belong to V prime, right, from the dual. So you need to multiply by V, right, some member in V, and then take the integration for the dual pair, right? So this one U prime multiplied by the test function, so you get V by that, right? And A T U multiplied by V, you get this, the bilinear form, right? And the other one is come from the integration by part here, and f of t is the dual pair with V. So I miss out that dual pair here. So this is the weak solution that we want to obtain, but the formula here need to be satisfied for all v in the Banach space, and phi is the test function from 0 up to t. All right. So the existence and uniqueness result for this differential equation is a standard result, and we can obtain that if we give initial condition U0 in the L2 space and the non-homogeneous term in this V prime like this, then we can obtain a unique weak solution. And also we have the following bound that the solution depends on the initial condition and the non-homogeneous term like this. Moreover, if lambda equal to 0 in our assumption, then we have some relationship of the norm in the Hilbert space with the norm in the Banach space V, like this. So this is a good estimation because we can see that the solution depends on the initial data and also the non-homogeneous term only. All right. So next thing that I want to talk about is when we consider the semi-linear equation, right? So different thing, we change f that depend on x and t to be depend on u itself as well. So you can see that u appear also in the non-homogeneous term. So this makes the equation become semi-linear equation. All right. So the thing that we need to deal with the nonlinear problem like this is that we first consider the homogeneous equation by putting the right hand side to be 0. So we put this function on the right hand side to be 0, and the operator has the same assumption as the previous section that I mentioned. So we can see that from the problem of existence and uniqueness, because the right hand side function, we can just put f equal to 0, you can obtain a unique solution as well. And we will write the solution that depend on the initial condition u0 to be u of s u0, something like this. So we write in this notation. What the thing that we change from the previous one is that we start the initial time at small time s rather than start at 0. So this solution will depend on the initial time that we start as well as the initial condition u0. So we write the solution in terms of this function here, this operator here. And this operator is really important. It is called the evolution operator. So for the evolution operator is the operator that define on the space V into V, like this, and it satisfies this evolution property. As if we want to have the evolution system that start from Ts, we can go from T to tau and from tau to S for the composite map of the operator like that. So that is usual, like the same idea as the one that you did for the case of autonomous system when you look at the semi-group property, something like that. But this one is the 2 parameter. And some research has been studied on the evolution system like this. And if we have the Dirichlet problem, we can estimate the norm of the operator from LP space to LQ space, satisfy some bound like this as well. So the evolution operator has a lot of use in order to study parabolic equation like this, right? So if you write evolution operator, then you can come back to consider the semi-linear equation. So as the moment as I mentioned, we consider the right hand side to be equal to be 0, right? Then we obtain the evolution system. After that, we can come back to study semi-linear equation. So we can write down the my solution of semi-linear equation in terms of evolution system like this. So the time that we start from S, right? So this evolution system, we use UTS at U0 and plus integral from S to T, U T tau, F tau, U tau, D tau like this for the right-hand side term. This is called the variation of constant formula that we will obtain the solution in terms of this formula. This is the weak formulation of the problem as well. All right. So because you can see that we want to find the solution U that satisfy this equation 5, and it appear that U is on the left hand side as well as on the right hand side as well. So in order to solve this, we just need to rewrite it and consider it in terms of a fixed point problem. So what we do is that we write the operator G that map from the function space into the function space. So we put G to be the right hand side of equation 5, GU equal to this term. If you get a fixed point, GU equal to U and U equal to the right hand side of equation 5, then you obtain a my solution of semi-linear equation. So that's why we need to introduce this map G in some certain space, right? For the variation of constant formula, and the problem will reduce to fixed point problem in order to find the existence and uniqueness of solution. So there's a lot of techniques, as many people from this workshop, they work on the fixed point. I think all of you should know there's a lot of techniques that you can use to solve this fixed point problem. So the standard one is the Banach contraction principle or the contraction mapping theorem. And the other thing that we can do with this is the iterative approach by study lower solution or upper solution by setting the space in a positive cone, something like that. Then you can get a sequence of solution that converge to a sequence of function that convert to a solution. Or we can study local solution and global solution and the blow up of this solution. So I just outline the simple case when we use the Banach contraction principle to obtain the existence and uniqueness of solution. A typical assumption that we need to put on the semi-linear term is the Lipschitz condition. Here we put f of tu minus f of tv in the norm v prime less than or equal to kr multiplied by the norm of u minus v like this for uv that less than or equal to r in the norm. So this is somehow like the local Lipschitz condition. If you have u and v has the norm less than r, then you have some constant that depend on the radius of the ball that contain this u and v. So if you use this locally Lipschitz condition for the nonlinearity, then you can show that the map that I mentioned here is a contraction on some time interval. Then you obtain the local existence of solution. So here, the theorem that I list here is that for a certain row with the initial condition has the norm greater than this number, there exists H positive such that you can find the solution starting from time S and go a little bit S plus H some time a little bit further from the initial condition. So this is the local existence. But if you use the same idea to extend the solution, then you can extend to get the maximal solution. So the solution will exist up to time t plus here. T plus here is called the maximal existence time. So we obtain a unique my solution up from time S up to this maximal time. So this is the standard technique that we will obtain the solution. So if you can extend further to the global time, then you obtain the global existence. But in some case, you cannot extend the solution further, that you can consider the problem of blow up for the solution as well. So there's a lot of direction of research that involve parabolic equation that we can consider. Okay. And I remark for the case that if we look at autonomous case, when the operator A does not depend on the time t, so A is just some operator that not involve the time t, then this is the autonomous case. The evolution system that I mentioned earlier is just reduced to the idea of the semi-group. So my solution can be written in terms of semi-group S t minus s u0 and integral from s to t of s t minus tau, and the right hand side, the semi-linear term like this. So this st is the strongly continuous semi-group generated by this negative a, this operator here. And if you remember that the property of the semi-group is like this, as the time t equal to 0 is just the identity, and they have the property of the composite like this. Right? It's same like the evolution system, but the evolution operator that I mentioned for the non-autonomous case is the two parameter semi-group. All right. So in fact, the part that I study in this parabolic equation is the one that I worked during the time that I studied PhD, but I consider the behavior of solution when we change the space or the domain of the problem. So I will talk about it later on throughout toward the end of this talk. So we move to the second part of my talk. The second part is the research that I did with my PhD student here at KMUTT. So after I work at the KMUTT, I also interested in fractional calculus. So I start to study about fractional differential equation. Firstly, I start by looking at the fractional ordinary differential equation, but later on, I just want to extend that to the parabolic equation that I worked before. So that's why it become the topic of fractional evolution equation here. So the concept of fractional order differential equation arises in many applications because they can use a more general derivative, because as you know that fractional derivative is somehow generalized from the concept of ordinary derivative, and it can be applied in various fields. And there are many definitions of fractional calculus, fractional operator. For example, the Riemann derivative, capital derivative, Hilbert derivative, and so on. So there's a lot of extension in this area. And the two main important definitions are the Riemann derivative and capital fractional derivative. And this has been used to modeling that has the memory effect. So the problem that depend on the previous time or previous state as well. So this is very useful when dealing with fractional derivative. So what I consider is that we can see that this equation looks similar to what I talked earlier at the beginning of this talk. When we change derivative, du dt to be the fractional order derivative, all the rest is the operator or the elliptic operator and the non-homogeneous term like that with this initial condition. So we consider the fractional evolution equation in this way in some Banach space E. So there are several results that study about this fractional evolution equation in terms of existence and uniqueness using various techniques that I mentioned earlier, using semi-group theory because this is a non-autonomous case, and somehow they also use many fixed point theory to study this problem. So the thing that I want to discuss in this talk is about the well-postnet problems. So the well-postnet is involve the existence and uniqueness of solution. So when we have differential equation, we ask the question that whether this problem has the solution, and if it has a solution, is it unique? So this is the first part of the well-postnet problem. And the second part is about the stability. So when we want to see that if you change the initial condition a little bit, or if you look it at some approximation of the problem is close to the original problem. So we look at the stability problem as well. All right. But what I'm going to talk today, I will focus on the fractional derivative that depend on some function phi. So this is called the phi capital fractional derivative. Right? So let me go through the definition of the phi capital fractional calculus. So we start with the function phi that is C1 function and is increasing with the derivative is non-zero. Then we can find the fractional integral like this 1 over gamma and integral from a to t. This phi is just some weight here, right? And multiplied by phi that t. So you have phi t minus phi s to the power alpha minus 1 for the fractional derivative of order alpha like this. But this one is more general from the capital or Riemann integral. If you put phi t equal to t, then it's become the classical one. So you get t minus s to the power alpha negative to the power alpha minus 1 here. It's just the standard version of the Riemann-Levin fractional integral. Or fractional derivative is defined the same way. For the capital one, you need to take derivative first and then take the integral like this. And some property that is useful in order to obtain the solution, we need to know that if you have derivative in terms of fractional derivative like this, when you apply the integral, what happened, right? In the standard calculus, if you differentiate and you integrate, you get back the function f, right? But here you have function f and some other term also come up from this integral. You apply the integral operator to the differential operator in the fractional calculus sense like this, right? And the other two that we need to use in order to obtain the existence of solution is the Laplace transform, because when we solve the equation, we need to apply the Laplace transform to the problem. So according to the definition of the phi function, we need to generate the Laplace transform that involve the phi function like this. So it looks like similar to the standard Laplace transform. If you put phi t equal to t, right, you will get t minus a like that. So that is the standard version of the Laplace transform. But here we have this term and also the derivative of this function for the Laplace transform that involve phi function like this. And our work here, we will consider two cases: the one that the semigroup that is compact operator, and the second case when we assume that the semigroup is non-compact operator, we will obtain the existence and uniqueness of solution and the stability in terms of Ulam higher stability sense. Then we conclude the well-postnet of problem. So here we generalize the evolution equation using this fractional derivative that involve the phi function, where the operator A, this evolution elliptic operator, is an infinitesimal generator of the C0 semigroup, this semigroup T like this, right? So the idea is that I need first to generalize the concept of solution, right? So you can see that what I did here, my solution can be written in terms of the semigroup like this, and it's also involve the fractional function phi in here. But the difficulty is that first of all, I need to change the semigroup that also involve the fractional calculus. So the idea is that for the standard evolution equation that I mentioned in the first part, we need to think about what happened to the semigroup in case that we consider the fractional time derivative. So we divide the new semigroup that depend on the fractional and the phi function, and we write my solution in terms of semigroup like this. So after we get the equation in terms of semigroup, then we can consider the existence and uniqueness in terms of fixed point problem as I mentioned earlier. So the assumption is that we mentioned earlier that operator of the semigroup we separate into two cases. The first one is the one that have compact operator for the semigroup, and the second one is non-compact operator. So here is the one with compact operator, and the function, again, we need somehow of the continuity and measurable property of the non-homogeneous term for the semi-linear term f, and some Lipschitz property like this, right? So the hypothesis H4 is the Lipschitz property, and the other property is to make the bound in order to get the Banach contraction, right? So if we assume all of that condition, we will find my solution when we have this condition 11 here. So the condition is to make sure that we get the Banach contraction. And we can extend the solution, as I mentioned, in the same way as parabolic equation. We can extend it into a maximal interval of existence. So we will find a solution from time 0 to T max. And if T max less than 0, then the solution will be blow up. So we can show that. And if we assume that condition, then we get the uniqueness, right? So for the existence and uniqueness is just follow from the fixed point theory. And we can also study about the global existence when we want the solution to exist for all time t from 0 up to infinity. We need to make some assumption to be H5 like this. The other thing that we consider is the stability of the problem. So remember that we consider the evolution equation in equation 12 when we change the derivative to be the fractional derivative, and that is the evolution system that we have before. But if we consider the inequality, right, we change the equal sign to inequality like this, and the inequality depend on what type of bound that we want. If we want to be less than epsilon or some function like that, then we will see that if we can find the solution that close to the inequality like this, then we have the type of Ulam higher stability problem. So the definition of Ulam higher stability is that if you have the evolution equation 12 is Mittag level Ulam higher stable, if you can find the constant C such that if you have the equation for inequality 13, then you can find the solution of 12 that close to the inequality like this. With this, the solution of equation and inequality are very less in terms of the distance. they are really close like this, right? And they have some generalized definition in terms of fractional calculus. So we use the MIGTAG function to be the bound as well. All right, and we can obtain the stability condition if we assume the Lipschitz condition for the non-homogeneous term for the function f. If the function f satisfies this Lipschitz condition, then we can show that the equation 12 is Ulam-Haier stable. Or if you assume more condition, then you have a generalized version, right? So if you assume this 3 conditions, then you have the generalized MIGTAG level Ulam-Haier stable as well. So that is the part that I am interested in at the moment, to extend the problem in terms of parabolic or evolution equation, and we want to consider the fractional calculus for the time derivative. All right. So I hope I have some time, a little bit, to continue the final part. This part, the last part of the talk, I will talk about something that I actually not an expert on this, but this is the one that I think after I talk about parabolic equation and fractional calculus, this is what the direction that we can go further. So the last part is about the optimization problem that involve solution of partial differential equation. All right. So the idea of optimization problem that involve solution of partial differential equation occur in many applications. For example, in the control theory for the shape optimization, when use in engineering, that you want to define what shape that minimize some function that you are interested in. So for example, in the application of drug delivery and also the electrowetting or EWAT device, the problem of optimization is that we want to minimize some functional, right? So we have J is a functional that depend on U and Z. U come from admissible set and Z also come from another admissible set here. Subject to this constraint, E U Z equal to 0, but the component of this one is look like the usual optimization problem, but U is called the state. So when you think of something that like differential equation, when you have some state that you want to measure the behavior of this thing, so U is the state variable here, and Z is the control variable. J is a cost function that you want to minimize, subject to the partial differential equation that your state and your control must satisfy, U and Z must satisfy. So the last equation here is the partial differential equation. So that means the concept of optimization here is that we want to minimize this functional, but U is the solution of this PDE. U and Z here that you want to minimize depend on partial differential equation, right? So let's have a look at some example to make you more understand on this topic. So I choose the example of optimal control for elliptic PDE. So we consider the minimization of this problem. JUZ is the functional that you want to minimize, is a half of U minus UD in the L2 norm and lambda on 2 of Z square norm. So why this, what is this one here? We want U and Z satisfy this partial differential equation. So this is the elliptic equation that divergence of AU equal to some function Z and U equal to 0 on the boundary. This is the Dirichlet boundary condition. So the idea is that U is the state because U satisfy the elliptic equation that we are interested in, but is depend on Z as well, because this one is the control, because you can put the control Z to control the solution U of the equation 7t, right? And the U is the state that depend on the partial differential equation here. And we want to minimize U. We want to obtain the solution of elliptic equation first, but the solution must satisfy equation 16. It means that we want to obtain the solution U of the elliptic equation that close to the target value. UD is the target value, right? And that is the control that you can put into the equation, and you can control it so that the solution you getting close to the desired state that you want. So this is somehow like control problem that used in many applications, because like when you want to drive some state to be the desired value, the state depend on differential equation, right? You can put the control set in, right? Make the solution or the state become closer to the desired state that we want UD here. So that's why we need to minimize this function, and why we have to input set into the functional here, because we want the control that not too big as well, because like in many applications you can put the control to suppress the state, but if the control set is too big, it's not good in application. That's why we need to minimize the norm of set as well, right? And we minimize the norm of state that close to the desired value that you want, as well as the control set is not too large as well. So that's why we need to minimize functional J that depend on the solution of partial differential equation like this, right? So the problem of this optimization that involves solution of PDE, the first step is that you need to make sure that the solution of PDE exists. So in this case, the elliptic equation here we can formulate in the weak sense as well, like this, right? And there is the theorem that we can obtain the existence and uniqueness of weak solution in terms of the function on the right hand side. So if you have the function Z on the right hand side, you put the control in, you get the solution U, right? So it's the same idea as I mentioned earlier, that when we have PDE, we first study about existence and uniqueness. Once you get the uniqueness here, then you can define the operator, which we call the solution operator, that you put the control, you get the solution U that depend on the control, because the solution here will depend on the control that you put in, right? So U depend on Z. And then you can reduce the optimization problem, because the function that you have to minimize the functional J depend on U and Z, right? But because you know that the solution, the state U depend on the control Z, so you can write U equal to solution that depend on Z. So it will reduce to optimize one variable Z here, right? So the problem become the minimization of the new functional, that you set the new functional to be the functional that involves Z here. And then you can obtain the existence and uniqueness of the optimization problem through the usual technique or other techniques that you can apply, like the convexity assumption, the lower semi-continuity assumption, in order to get the convex optimization of this problem as well, right? The last example that I want to show you is the one that relates to the topic that I studied during my PhD, when I consider the effect of the domain of the partial differential equation on the solution. So this topic is about shape optimization problem. So shape optimization problem is the problem that involve finding the shape that minimize a certain chord functional, right? So the problem is that we want to minimize functional J that depend on the geometric shape of the domain omega. So we want to minimize J that depend on the domain. So if you have some space, the shape of domain, you get the solution of the PDE that depend on that domain, and you want to minimize some functional that depend on the domain. But the functional that depend on domain usually arise from solution U that depend on the solution of the PDE. All right. So for example, this is the shape optimization for the elliptic case, minus Laplacian U equal to F and U equal to 0 on the domain. So for the Dirichlet boundary condition like this, then we obtain the solution here, right? Because this is the standard existence uniqueness. We solve for the elliptic equation, you obtain the solution in some Banach space, and this is called the state. And we want to consider the minimization that depend on the integral of the solution. So the functional that we consider depend on the domain omega, and omega range from the admissible set of the domain. So some example of the functional that involve the domain is the norm of the gradient like this, or the norm of gradient square divided by the norm of U square. This one has the spatial property is called the eigenvalue, the first eigenvalue of this elliptic problem. So there's a lot of research in this area that depend on the functional that you want to consider. The optimization on the shape of the domain is become something that you can extend the study from existence and uniqueness of the solution of PDE. So here I just discussed the case of elliptic case, but what I want to do in fact, that is the research plan, my research plan. I want to extend this one to the case of parabolic type equation. All right. So I think that should be the end of my talk. Thank you for your attention.
Thank you very much, Ajahn Parinya, for your very nice talk. Okay, so are there any questions from the audience? Any questions?
Oh, hello.
Yes, Tala?
I want to ask 2 questions.
Yes.
First of all, thank you very much for this interesting talk. I want to know that Ajahn Parinya mentioned about Laplace transform. So I want to know that is there any condition to apply Laplace transform to any function or PDE, or we can simply apply to any arbitrary PDE?
I'm sorry, I can't catch your word very well. What condition that you mentioned?
I mean, I want to know that if we want to apply Laplace transform to any function or any partial differential equation.
Apply what? Sorry, I cannot catch what.
Laplace transform.
Oh, Laplace transform. Okay.
So is there any condition that a certain function or PDE must satisfy to apply the Laplace transform?
Yes. There should be some condition in order to apply the Laplace transform, because the idea of solving partial differential equation, usually you apply the Laplace transform, right? But when I mention about the fractional Laplace transform, it depends on the definition of the fractional calculus that you work on as well, and it depends on the bound as well. If the function does not have some property, then you cannot apply the Laplace transform. So you need to check those conditions.
Oh, okay. And my second question is that if we have a boundary value problem with the system of partial differential equations, maybe 2, 3, 4, so or maybe one partial differential equation pertinent to a particular physical problem. Okay. So how we can ensure that this PDE has a unique solution in that particular domain?
In the particular domain. So yes, for the existence of solution, when we study the existence of solution, usually I will use the fixed point theorem that guarantee the existence as well, because I want to use the uniqueness property later on. So that's why when you derive and prove the existence, you need to choose the two that guarantee the existence and uniqueness at the same time. But if you only want to get the existence, then you can use other fixed point techniques to show. So it
Okay.
depends on what kind of thing that you want to use later on. But for me, I need to guarantee the existence. Otherwise, I cannot use this to prove other properties. So sometimes I need to assume some strong condition in order to obtain the uniqueness. But if you work on like multi-value function, then you might not need the uniqueness, right? So you can obtain the solution set and you use that solution set to do something later on. So you may not need, it depends on the problem that you will work later on, I think.
Okay, thank you very much. One last thing, that if as you mentioned that we do the stability analysis and uniqueness and existence. So if one is working on the modeling of physical phenomena,
Mm-hmm.
so we have particular system of PDEs with initial and boundary conditions, but we are interested on the behavior of maybe on the behavior of the functions involved in that modeling phenomena.
Oh.
So is it compulsory to do the uniqueness and existence, because we are only interested in the behavior? So
Okay.
if we can solve the system and find the solution, and these solutions are satisfying the conditions